All right, friends and neighbors, welcome back to another networking video. Now, this is technically not networking. Actually, I could say technically it is networking because I realized that we were sort of skimming over one of our topics when we went through our home network build, and that was antennas. So when I cavalierly held up things like this Belkin and said, oh, it's got internal antennas, or I held up the Linksys, right, with its external antennas. I didn't talk about the antennas at all. I just said inside and outside. And it turns out that there's an awful lot that we can talk about when we start thinking about antennas. And so that is what we're going to do today. So what is an antenna? Well, an antenna is really a conductor. If you took the cover off of one of these, you would find out that it's just a piece of copper in there, not unlike a coat hanger or a piece of wire. It's just copper, but it is of a particular size and shape for the application. And so I'll talk about that here in a second. Now, antennas are actually kind of magic too, because through the mystical magical property of skin effect, we take a radio, which is an electrical device, and we generate a signal. So the radio generates the signal and it sends it out to a wire, and mystically, magically, that signal is propagated through the air. Now, there's a big difference in wireless communication between RF signals and optical signals. And of course, when we're talking about 802.11 or 802.15, we're really talking about RF signals. And so we have to sort of remember that. But it's electrical right to the time it gets to the antenna. And the antenna converts that electrical signal to RF. Now, the physical dimensions of an antenna make a difference. So these antennas, right, I can hook up a bunch of antennas to these. Now, these aren't easily removed on this particular Linksys, but a lot of them you can remove them, and it's just a typical RNC connector. Now, but the antennas are of a particular length, usually what we're talking about here, and even a physical distance apart. So the image above me here, that's a Cisco access point, and you can see that on one side the antennas are close together, and on the other side they're farther apart, and they're of different sizes. That's because one side is 2.4 gigahertz and the other side is 5 gigahertz. Now I've got this little formula down here. Very commonly the antenna is 1/2 of the wavelength. That's what we call a half-wave dipole. And the reason, by the way, I put a rubber ducky on the front of this video is because a lot of times we call the dipoles rubber duckies. But the antenna, the physical length of the antenna is directly proportional to the wavelength of the frequency. And so the higher you go in frequency, so the two things are related. So the higher you go in frequency, the shorter your wavelength is. And so the lower you are in frequency, the bigger the antennas are going to be. That's why when you look at radio station antennas, they're enormous because the frequencies are much, much lower. But the 2.4 gigahertz frequency is only about 5 inches long, and 5 gigahertz is even smaller. So that's why 5 gigahertz antennas are usually smaller. In this particular case, you can also see the physical distance between them, and that is because these are what we call diversity antennas. It's trying to pick up the best signal, and so the antennas are one wavelength apart. So that's why that is. Now, when we start talking about antenna characteristics, we've got a lot of things that we could talk about. Active versus passive. Most antennas are passive, meaning there's no additional power supply for an antenna, although you can have an amplifier in there. Antennas are very passive, and they're just metal configured for the size of the waveform or the particular frequency that you're after. And so this right here, the C is the speed of light, and then we've got the speed of light is equal to the wavelength times the frequency, and so that's why they're inversely proportional to each other. And then we've got things like the shape of the antenna, We have whether or not your antenna is one-dimensional or designed to propagate in 2 dimensions. So we want to concentrate the energy in some way. Most of the antennas that you see today are what we call one-dimensional antennas, omnidirectional, and so we're not focusing the energy in any particular place. Now, height can make a big difference, especially if we're talking about outside propagation, but inside, really what we're worried about is location. Now, you can cause problems for yourself if most of your nodes are on the second floor of a building and your access point or your antennas are in the basement. That might actually create a problem. And so that's why we say when we're doing a site survey, well, I'm going to think about where I'm computing, put it close by there and see what my signal strength is and experiment with various locations. Now we've got a couple of other terms here. There are, generally speaking, 2 flavors of antenna. We have omnidirectional radiators, or those that radiate energy in all directions, 3-dimensional, evenly spaced sort of thing. And then you've got directional. So the dipoles and things like this, these are going to be omnidirectional. And so the energy propagates equally in all directions. And so those are our dipoles and our half-wave dipoles. Half-wave just means that the antenna is 1/2 the wavelength. There are lots and lots of directional antennas out there. Anything that's got a dish or a horn, or you've seen maybe the Bluetooth snarfing guns, the Yagi antennas, where you put a gun stock on an antenna and you aim it someplace. That's a Yagi antenna. That's very, very directional. So these are examples of antennas that are trying to concentrate the energy in a particular direction. But that also means that the energy falls off significantly in the other direction. Now, some key terms when we're talking about antennas. Antenna gain is a really, really important idea. Now, these have actually very, very small gain. When we look at the internal antennas on something like this, very, very small gain. Typically what we would say 2 decibel gain. Remember from our thumb rules, 3 decibels is doubling the power. So 2 decibels is less than a doubling, and remember that's very, very local to this. Now something like this has a 2 decibel gain or 2 dB gain, but sometimes there's an extra letter. So it'll say 2 dBi or 2 dBd gain. And that is a relationship or a reference to some other kind of antenna or radiator. So dBi means it's a comparison to an isotropic radiator, and dBd means it's a comparison to a dipole regulator. Well, if you're comparing one antenna to another, it's very common to compare something to this, right? If I put in a different kind of antenna here, how is it going to compare to this antenna? And so that would be dBd. dBi is isotropic. It's a little more confusing, but there is really only one kind of perfect or isotropic radiator that we know of, and that is things like a star or the sun. But some antennas get kind of close to that, meaning that they radiate energy equal in all directions. So sometimes we compare an antenna to a theoretical isotropic radiator. Now, polarization is a really, really important idea. If I took this access point and I had a certain signal strength, and then I turned all of these antennas, right, to be polarized or oriented in a different direction, well, I would get a different signal strength. So the orientation of your antenna makes a difference, especially if we're talking about directionals. Now, this is why we say sometimes antennas are polarized in a particular direction, and we see the example of polarization everywhere. Old TV antennas, polarized sunglasses, things of that sort. Whatever your polarization is, they should be the same for the sender and the receiver. Now, another thing to think about is the radiation pattern. I'll show you a couple of radiation patterns at the end of the video here, but a radiation pattern goes directly to our reception. If I'm trying to shoot a long way away, I want a directional radiator, but that means other areas are not going to get the same signal strength. If I don't know where I'm going to be, or I want to cover some area, then I want a radiation pattern that spreads out. Now, related to the radiation pattern, particularly when we're talking about directional antennas, is that we've got a beam. You can sort of think about the energy as a beam heading in a particular direction for directional antennas, Yagi, patch, right? Um, but alongside of that, we get what are called our lobes. So our main beam is called the main lobe, or the main part of the energy. And then you've got areas to the side, we call those the side lobes. Beam width is how wide that main lobe or the main beam width is. And so we can measure that with an angle. And some antennas are very directional, pinpoint, right? They send it a long way, but a really narrow beam width or really narrow main lobe. But if we have an antenna that's just designed to generate energy in a particular direction, then the angle of the beam is much, much wider, and its propagation distance is also going to be shorter. And then we have bandwidth, which is the range of frequencies over which an antenna will perform well. You can't just hook up any old antenna and hope that it'll work. These are great for these particular devices. But if I had a much larger antenna, or if I was dealing with different frequencies, right, I wouldn't get the same kind of performance. All right, now as promised, we have a couple of radiation patterns for you. Now here, up in the, well, right above me is a patch antenna. It is a directional antenna. And a lot of times we think about antenna radiation patterns from both a horizontal view, if I'm looking at the side, right, what does the energy look like? Or if I was looking straight down, what we might call the bird's eye. So if I'm looking at this horizontally, I can see that I've got an energy pattern mostly on one side of the antenna with a little bit of bleed back on the back side. So a patch antenna has sort of a broad beam width, but it doesn't propagate, an extraordinarily far distance. And then if I was looking at the side of this, I would also recognize that there's a certain angle for the vertical direction too. And so if I fall inside the horizontal and vertical beam width, then I'm in good shape. Now this contrasts to the dipole antenna direction. Now this is a Cisco antenna here, and here is the orientation or the radiation pattern around that antenna. And so you can sort of imagine that right in the middle here is the antenna, and then it radiates in this sort of blob. But this is a three-dimensional blob. That's why I included this one here. So it is energy all the way around the antenna. But it's not perfect, right? It's not straight up and straight down. It falls off quite a bit as you go vertical or in the, upper vertical or lower vertical. And this is why sometimes the dipole antenna pattern is called a squashed donut, because it doesn't propagate in a sphere. It is sort of squashed on the top and bottom. So that is the radiation pattern around a dipole. This is also why if you're located too far above or too far below your access point, your signal will fall off. Well, there we go. There was some antenna goodness. Now, for your home, does it really matter? Not really, because you're almost always going to get, your dipole antennas that are half wave or full wave dipole. They're omnidirectional radiators, and they'll have a small amount of gain associated with them. They might be internal, right? Your laptop has an internal antenna that works really well. A lot of times they're on the screens of the laptops. But there you go. But if you are doing an enterprise deployment, if you're responsible for covering outside areas or shooting between buildings, things like that, well, the style of the antenna can make a huge difference on performance, especially when we start talking about the concentration of energy, so the type, the gain of a particular antenna, and the location of that antenna. Hey, like and subscribe if you dug the video, and especially if you did this during the course of the video. We got to remember that when we're building networks, sometimes there's these things that are kind of on the periphery, but they actually can make a big difference in the performance of our networking. When we start talking about wired networking, right, we talk about all the equipment, but we got to worry about the wiring. What kind of copper are we putting in? And with a wireless network, what kind of antennas are we dealing with? Well, whether you decide to go omnidirectional or unidirectional, may those packets always reach their destinations.